In this video, I'm going to find series solution for a differential equation that has a singular point. The problem is rather long, so first I'd like to give you the different steps that you need to take in order to solve this problem. Okay, so these are the steps you need to take. Step 1, you express the differential equation in this format, which is y double prime plus p of x times y prime plus q of x times y is equal to 0. You can do it by dividing both sides of the differential equation by the coefficient of y double prime. You may actually be given the differential equation already in these formats. In that case, you don't have to do anything. Second step, determine the singularity type, whether the singularity is regular or irregular singularity. How do you figure it out? The regular singularity is going to be having these two conditions satisfied. Limit x approaches x naught, okay, x minus x naught times p of x. This limit will exist. Now x naught is the point that we are talking about, the singular point, all right? So this limit exists, and limit x approaches x naught, x minus x naught whole square times q of x. That limit also exists. If both of these limits exist, then we call the point x naught to be a regular singular point. If you have a regular singular point, then you can find the solution, series solution. And how is that solution going to look like? That's how it's going to look like. Y of x is equal to x to the power r times summation n is equal to 0 to infinity a sub n x to the power n. And I can bring this x to the power r inside the summation. That's going to give me x to the power r plus n. Now you have a y, or a solution, or assumed solution. Now you can go ahead and find y prime and y double prime. That means the first and the second derivative of y. Once you have found the y, the first and the second derivatives, what do? You take these three values and plug it into the given original differential equation. Once you plug in the values of y, y prime and y double prime, you will come up with an equation that has a bunch of summations in it, okay? You want to combine the summations that have the same power of x, okay? It will have something like x to the power r plus n. And there will be a summation, one or more, that will have power other than r plus n. Okay, so summations that do not have the power of x to be r plus n, what you need to do, so this is an important step, you need to shift the indices of those summations so that the power of x becomes r plus n. We want to have all the powers of x on the left hand side to be exactly the same, okay, so that we can compare the coefficients on the left with the coefficients on the right for the same power of x. All right, so shift the indices so that x has the power of r plus n, like the other summations. Now, if you shift the indices, the starting points are going to change, okay? So in that case, you'll have to evaluate for one or two terms. In most cases, you'll probably evaluate one term, in some cases two terms, okay? The first term, when you evaluate the first term, which is going to be for n is equal to 0, by the way, you'll get the initial equation, okay? Then if needed, you may have to evaluate the second term, which is n is equal to 1, all right? Then you will have an expression where you will have one or two terms and then two summations or more than two summations that have the exact same starting point. It starts at the same point for same n value, okay? Now, we have done it, so here, make sure by shifting it, we have all the summations starting at same value n, okay? And once you have it, by the way, you're gonna get a formula by comparing the coefficients on both sides. That's gonna be the formula which you're gonna be using to find the coefficients, okay? And it's a recursion formula, or that means it repeats itself. Now you use the recursion formula to find the coefficients for different values of n. Let's say n is equal to 1, 2, 3, 4, 5, 6, etc. They'll give you the coefficients. Once you find the coefficients, then you go back to the original assumed series solution for the differential equation and plug in those coefficients into the equation. That will give you the final solution. So now what I'm going to do, I'm going to go ahead and solve an actual problem. I know it's like bunch of steps, but if you follow the problem a couple of times, if you look at the video a few times, it'll start to make sense. It'll all come together. It's not as bad as it looks. Now the problem that I'm going to solve is this. This is the differential equation that we're going to solve. Xy double prime plus y prime minus 5y is equal to 0. Our first step. So I'm going through the steps that I just described. There are 11. Actually, there should have been 10 steps, not 11. I just skipped one number there. Anyway, so I'm going to go over the steps. So first step was to go ahead and convert it into the form y double prime plus p of x times y prime plus q of x times y is equal to 0. This could be achieved by dividing the original or given equation by x, because coefficient of y double prime is x. So that gives me this value. And from this, we can read off the coefficient of y prime, which is just 1 over x. So your p of x is 1 over x. And read off the coefficient of y, which is negative 5 over x. So your q of x is negative 5 over x. Now, what we are going to do, since we found the p of x and q of x, we check the singularity. The singular point x naught is equal to 0, right? So that means there is a singularity at 0. Now, is this singularity a regular singularity or an irregular singularity? If it's a regular singularity, we can find the solution. If it's irregular, we can't. So now, the way to check it is to take the limit. So limit x approaches 0, x times 1 over x, and I have written it before, but let me go ahead and write it again. Limit x approaches x naught, x minus x naught times p of x. This limit does exist, as well as along with the top limit, limit x approaches x naught, x minus x naught whole square times q of x. That limit exists as well, okay? So that means both of these limits exist. If that is the case, it is going to be a regular singular point. That means x naught is a regular singular point, okay? Limit exists means, by the way, this is analytic. That's what it means. X minus x naught times p of x is analytic, and similarly x minus x naught whole square times q of x is analytic. And what is analytic? It's basically a function that is differentiable in the complex plane. That's what it means for a function to be analytic. All right, so we just take the limit of the first one, which is x minus x naught, but x naught is 0, so it becomes just x times p of x, and is nothing but 1. Similarly, limit x approaches 0, x squared times negative 5 over x. If you simplify it, you get q naught. All right. Now, this p naught and q naught, these are the values that you could use to find the initial equation, okay? And I did it in a different problem, but I did it slightly differently than this way, okay? I actually took the solution and inserted that into the original equation, but here I am using a slightly different version of the approach where P naught and Q naught is given. So the first limit is called P sub 0, second limit is called Q sub 0, lowercase both of them. And then your initial equation would be R times R minus 1 plus P naught or P sub 0 R plus Q sub 0 is equal to 0. So we found P sub 0 to be 1, so we just plug it in 1. So and Q sub 0 is 0. That's going to give me R square minus R plus R is equal to 0. R square is equal to 0, so R1, R2 is equal to 0. That means roots of the initial equation repeat, okay? So the same root. Now, in this situation, my solution is going to be of this format. Y of x is equal to x to the power r times summation n is equal to 0 to infinity a sub n x to the power n. However, my r is nothing but 0, right? So this equation in essence boils down to y of x is equal to summation n is equal to 0 to infinity a sub n x to the power n, because x to the power 0 is going to be 1, okay? And now, remember, it's not x is not 0. It's not 0 to the power 0 because we are evaluating on the series solution near the singular point. Okay, near the singular point, remember that. So let's go ahead and solve it. But in another problem that I worked on, over there I actually took this y and found the y prime and then y double prime, and then I took these three values and plugged it into the original equation and then kind of manipulated the coefficients so that, manipulated the power of x so that I can combine the summations, which you will see, by the way, shortly. And then I went ahead and set n is equal to 0, okay? And that gave me the initial equation. But here I'm doing it slightly differently. But anyway, it's your preference. You could go ahead and use this. Just take this equation, take this little formula, and then plug in these values, and you'll get the initial equation. Or you could take the y prime, and y double prime, and plug it in here, and then simplify it, and set n equal to 0, and the coefficient of x sub x to the power 0 is going to be giving you the initial equation. Given that, of course, a sub 0 is not equal to 0. So let's go ahead and continue with this problem here. We found R1 and R2 to be 0, right? So my solution is going to be of this format. Y is equal to x to the power r times summation n is equal to 0 to infinity a sub n x to the power n. However, since r is equal to 0, x to the power 0 is going to be, or x to the power r is equal to x to the power 0, which is just 1. Remember, x is not equal to 0, okay? Because we are kind of evaluating near the singular point or near singularity. So we are avoiding the 0 to the power 0 situation, okay? So in reality, this equation then becomes is nothing but y is equal to, or if you can call it y1, doesn't matter, let's call it y1, okay? Is going to be summation n is equal to 0 to infinity a sub n x to the power n. And this is exactly what I have here. Just x to the power r becomes x to the power 0. Now, the things that I was talking about, I'm going to have to do this. Find the first derivative, which is this, right? Find the first derivative of y1 and find the second derivative of y1, which is pretty straightforward. You can see what it is. First derivative is n times a sub n times x to the power n minus 1. Second derivative is n times n minus 1 a sub n x to the power n minus 2. And I'm going to take these values of y1 y1 prime and y2 prime and plug this into the original equation. If I do that, this is what I get. Just look, you have an x here, y double prime. I found y double prime right here. I just plug in the y double prime. Then y prime, which is this, that is the same as this, minus 5 times y. 5 times y, or y1 rather. Okay, so that's going to be this. Now I kind of go ahead and combine like terms. Okay, so let's go ahead and check it out. If you multiply this x with x to the power n minus 2, you're going to get x to the power n minus 1. And this has x to the power n minus 1, and this will have x to the power n minus 1. So I could combine these two summations and get this one. So summation n times n minus 1, this, plus n, this, times a sub n. A sub n is common to both, times x to the power n minus 1, which both of these summations will have. Okay, remember, even though this is x to the power n minus 2, because of this x is going to be x to the power n minus 1. So now we have to look. Here you have x to the power n minus 1, but here you have x to the power n. So we kind of have to shift the indices, right? So the way I do it is shifted by 1. So anytime you see, so in this summation, anytime you see n, replace it by n minus 1. So let's go ahead and write it out here so that you can see what I'm talking about. N is equal to 0 to infinity 5 a sub n x to the power n. Now I'm going to replace n by n minus 1. So summation, there is an n here, so I'm going to put n minus 1 is equal to 0 to infinity. Then the number 5 is there, just constant. A sub n now is going to be a sub n minus 1, right? Then x to the power n now is going to be x to the power n minus 1. Now this, by the way, is the same as saying summation n is equal to 1 to infinity 5 a sub n minus 1 times x to the power n minus 1. Okay, that is gonna make the power of x the same in all the summations on the left. Okay, here in this one, all the summations on the left. Now this is the calculation or the shifting that I showed you right here is done right here. So we took this and we converted it into this. Now if I plug in n is equal to 0, okay, if I plug in n to be 0, what happens? So where do I plug in n to be 0? You plug in n to be 0 right here. Okay, this is the one where you have the shifted indices, right? For the right summation and for the left summation, the index starts at 0. For the right summation, index starts at 1. So if we isolate, if we take out the first term from this one, which is n equal to 0, in that case, what's going to happen, the remaining terms are going to be aligned. That means this is going to start from 1 because we have taken the n is equal to 0 case, and this is starting at 1, and now both are aligned. We can compare apples to apples. If you plug in n equal to 0, what happens? You have n square a sub n, right? Okay, n square a sub n. So 0 square times a sub 0 is equal to 0. So that tells you that a sub 0 is an arbitrary value, okay? Because 0 times any fixed number would give you 0, all right? Okay, now for n is equal to 1 to infinity, now we have both of these summations. The first one is starting at n is equal to 1 because we already have taken into consideration n is equal to 0 case. That gave me the term a sub 0, right? For n is equal to 1 here and also n is equal to 1 here. So I can compare the coefficients of on the left side with those of the coefficients on the right side for the same power of x. So on the left side, you have n square a sub n minus 5 times a sub n minus 1. Okay, for x, that's going to be the coefficient on the left. X to the power n minus 1, that's going to be the coefficient. Now, on the right-hand side, you have only 0, so the coefficient must be 0. Okay, on the right-hand side. So that tells me that this thing is equal to 0, which leads me to a sub n is equal to 5 times a sub n minus 1 over n square. Remember, this is true for n greater than or equal to 1. Now, this is my recursion formula. Okay, now I apply the different values of n. When n is equal to 1, I get this number. Okay, just plug in n equal to 1, you get 5a0 over 1 square. N is equal to 2, you get 5a1 over 2 square, but a1 is something you already found right here, right? You plug in this value here to get the final value, which is 5 square over 2 square times 1 square a0. For n is equal to 3, again you do the same thing and plug in the last value a2 to get the final value here. For n is equal to 4, again the same thing and find the value. Remember, we are finding one value and using that value to find the next value. We are finding one coefficient, using that coefficient to find the next coefficient. So that's why we call it kind of recursion formula or recursive formula. So if you keep doing this, you realize that the nth term is going to be, nth coefficient is going to be a sub n is equal to 5 to the power n divided by n factorial square. Okay, n factorial whole square times a0. So your solution is going to be y1 of x, a0, the first term, remember? We took it out, a0 plus summation n is equal to 1 to infinity a sub n x to the power n. That's going to be the solution. So it's going to be a sub 0 plus summation n is equal to 1 to infinity. Pay attention where the indexing begins. N is equal to 1 to infinity. But a sub n, we just found it right here. 5 to the power n over n factorial whole square times a sub 0 times x to the power n. If I factor out the a sub 0 from here and here from both of these terms, I'm going to have y1 is equal to a sub 0 times 1 plus summation n is equal to 1 to infinity 5 to the power n over n factorial whole square times x to the power n. And that is your first solution. Okay? That is the first solution. Now, there is a second solution as well. In this case, remember our roots are equal. That means R1 is equal to R2 is equal to some constant. In our case, it was 0. Okay, initial equation has the same roots. So what is going to be the second equation? As it turns out, the second equation could be found in terms of the first equation. That means second series could be found in terms of the first series. So second series, y sub 2 of x, so we found y1 of x, y sub 1, right, is going to be equal to, so y sub 2 of x is going to be equal to y1 of x, which we already found here, times ln of absolute value of x, plus absolute value of x to the power 0, because the roots are 0, right, which is basically 1, times summation n is equal to 1 to infinity b sub n x to the power n. Now, in this equation, you kind of know everything except for this b sub n's. We need to find the b sub n's. Now, to find the b sub n's, you do the exact same process that we did for y1. We found y1, remember? We found y1, then we found y1 prime, then we found y1 double prime. I took these values and plugged these values into the given equation and then simplified. You have to do the exact same thing for y2. That means take the first derivative of it, second derivative of it, plug it into the original equation or the original differential equation given, and then simplify it to find these b sub n's. However, I'm not going to find the derivatives for this and then substitute it. It's a little bit of a messier calculation. By now, you probably realize that this problem is quite long and it involves a lot of calculations. Even though it's not hard, but it takes a little bit of time to get used to it, okay? If you look at the problems 2-3 times, it will start to make sense. So please don't get frustrated, don't give up, okay? Hang in and look at it a few times, you will just be fine. It will start to make sense. At the end, you'll be happy that you did. You'll really have a good understanding. I hope that this discussion was helpful. Thank you very much.